The universe is about 13 billion and 800 million years old, and we humans have dreamed of travelling through it ever since we first looked up at the sky. But there is something Einstein discovered over 100 years ago that changed everything. Nothing can travel faster than light. And here is the terrible problem. Even travelling at the speed of light, it would take us more than 4 years just to reach the closest star to our Sun. To cross our own galaxy, it would take 100,000 years. And the universe we can see is so big that light takes more than 90 billion years to cross it from one end to the other. Why did nature put this limit that seems to trap us forever in our little corner of space? Get ready to fall asleep while listening to this video. Subscribe to the channel, leave your like, and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Imagine for a second you could point a spacecraft at any star, push the throttle to the max and just go. The reality is the universe has a speed limit, and it's not one we can negotiate with better engineering. That limit is the speed of light, and it's not merely a barrier. It's a fundamental rule woven into the fabric of space and time itself, dictating the terms of any possible journey beyond our solar system. This concept comes from Einstein's theory of special relativity, which isn't a suggestion but a description of how things actually work. The key takeaway is that nothing with mass can ever reach, let alone exceed, the speed of light in a vacuum. This speed, roughly 300,000 kilometers per second, is the ultimate cosmic constant. Think of it less as a wall and more as a transformative rule. As an object moves faster, its mass effectively increases from the perspective of an outside observer. To push it closer to light speed requires exponentially more energy. To actually reach light speed would require an infinite amount of energy, which is clearly impossible. This means that every single idea for interstellar travel, no matter how advanced, must operate under this strict regulation. Our dreams of zipping around the galaxy like in science fiction are immediately grounded by this one simple immutable law. It forces us to think in terms of centuries and millennia, not years. Accepting this is the first and most crucial step in understanding the true scale of the challenge. It's not an engineering problem to solve, it's a condition to adapt to. So, if we can't go faster than light, what does that really mean for a trip to even the nearest star? Let's put it in perspective. Our nearest stellar neighbour, Proxima Centauri, is about 4.24 light-years away. A light-year is the distance light travels in 1 year, which is approximately 9.5 trillion kilometres. Now, if we could build a probe that travels at 90% of light speed, an astonishing feat far beyond our current capabilities, it would still take over 4.7 years from Earth's point of view to get there. That's just for a one-way trip for a tiny uncrewed object. For a crewed ship, which would be vastly heavier, achieving such a speed is a whole other magnitude of difficulty. But here's where it gets even more interesting from a physics standpoint. That travel time of 4.7 years is what clocks on Earth would measure. For the hypothetical travellers on that ship moving at such a high fraction of light speed, time itself would slow down due to an effect called time dilation. Their journey might feel subjectively shorter. However, this doesn't magically make the distance smaller for everyone else. It creates a strange paradox where the travellers return to a future vastly different from the one they left. This is a central, mind-bending consequence of the light speed limit. It doesn't just limit speed, it warps our very understanding of time and simultaneity. The energy requirement is the next monumental hurdle. Because of the way relativistic mass increase works, the energy needed to accelerate a ship climbs exponentially as you approach light speed. To get a modestly sized ship to even half of light speed, it requires an amount of energy that dwarfs our entire planetary civilization's current output over many years. Pushing to 90% or 99% requires energy budgets that seem almost mythical. We're not talking about refining rocket fuel, we're talking about harnessing the total energy output of stars. Concepts like matter-antimatter annihilation or controlled fusion are theorized as possible ways to achieve this, but they are far from practical realization. Matter-antimatter propulsion, for instance, would require producing and storing staggering amounts of antimatter, a substance we currently create in infinitesimal quantities in particle accelerators at immense cost. The storage alone is a nightmare, as antimatter annihilates upon contact with normal matter. So the problem isn't just about going fast, it's about finding the power to pay for that speed. This energy barrier is arguably as fundamental as the speed limit itself. Given these colossal constraints, the idea of human crews travelling to the stars becomes incredibly problematic. Our bodies are fragile, evolved for the gentle conditions of Earth. A multi-year journey at relativistic speeds would expose astronauts to intense cosmic radiation, the kind our planet's magnetic field usually shields us from. Shielding against this on a spacecraft adds enormous mass, which in turn requires even more energy to propel. Then there's the psychological factor, confinement, isolation, and the knowledge that you are irrevocably separated from Earth, with communications taking years each way. For journeys lasting longer than a human lifetime, you'd need a generation ship where people are born, live and die during the voyage. This introduces staggering sociological and biological challenges, from maintaining a stable closed ecosystem to ensuring genetic diversity over centuries. The spacecraft ceases to be a vehicle and becomes a fragile, travelling world of its own. This leads many scientists to believe that if interstellar exploration happens at all in the foreseeable future, it will be done by machines, not humans. Robotic probes can be smaller, tougher, and don't need life support. They can be designed to hibernate for centuries and then awaken to collect data. They can take risks no human crew ever could. Our emissaries to the stars will likely be sophisticated AI housed in radiation-hardened casing, sending back precious data bits over the vast, silent distances. They represent a more realistic, though less romantic, path to the stars. But wait, you might be thinking, what about the cool ideas in movies? Warp drives, wormholes, hyperspace jumps. These are concepts that appear in theoretical physics, often as solutions to Einstein's later theory of general relativity, which deals with gravity and the curvature of space-time. A wormhole, for example, is a theoretical tunnel through space-time, a shortcut connecting two distant points. The problem is, while the math allows for such things, they would require forms of matter with exotic properties, like negative energy density, to create and stabilise them. Such matter has never been observed, and its existence is purely speculative. A warp drive, which would contract space in front of a ship and expand it behind, similarly relies on this exotic matter. The energy requirements for these concepts are also astronomical, perhaps requiring the mass energy of entire planets or stars. For now, and likely for a very long time, these remain in the realm of thought experiments and science fiction. Basing our hopes on them is, at present, like waiting for a miracle. So we are left with the stark reality of the light speed limit. It defines our cosmic neighbourhood. It tells us that the stars are not destinations in the sense that Paris or Tokyo are. They are remote islands in an ocean that takes lifetimes to cross. This limitation has a profound philosophical implication. It might be the universe's way of compartmentalizing life and civilizations. Perhaps it's a form of cosmic quarantine, preventing the rapid spread of species before they reach a certain level of maturity, or perhaps it's simply a neutral fact of physics with no deeper meaning. It forces a certain humility upon us. We cannot conquer the galaxy in the classic imperial sense. We can only patiently, slowly send out feelers. This leads to another practical dilemma known as the weight calculation, or the paradox of obsolescence. If we launch a generation ship today using our best current technology, a voyage lasting thousands of years, it is almost certain that technology on Earth will continue to advance. A newer, faster probe launched a century from now could potentially overtake the original ship, rendering its multi-millennium struggle pointless. Why commit to a 1,000-year journey when waiting a few hundred years might yield a technology that makes the trip in a fraction of the time? This logic can perpetually delay any actual launch, pushing the goalpost forever forward. It suggests that a truly transformative breakthrough, a fundamental change in our understanding of physics, might be a prerequisite for serious interstellar travel. In the absence of such a breakthrough, our exploration will likely remain local, within our own solar system, or observational. And this is perhaps the most important point. Exploration does not require physical presence. The revolution in astronomy over the past few decades has shown us that. With tools like the James Webb Space Telescope, we are analysing the atmospheres of planets orbiting other stars, peering back at the first galaxies and unravelling the history of the universe. All from here, our understanding expands with every new observation. We're exploring the cosmos with photons, the very particles that define the limit we cannot break. the future of human experience in space may lie in increasingly immersive virtual reality, fed by real data from robotic scouts, allowing us to walk on distant worlds without ever leaving Earth. The ultimate journey might be one of the mind, not the body. The speed of light, therefore, is not just a barrier, it is a teacher. It teaches us about the true nature of space and time. It teaches us about energy and scale. It forces us to think in terms of generations and millennia, challenging our short-term perspectives. It pushes our engineering to its absolute theoretical limits. And ultimately, it may redirect our ambitions from conquering vast distances to understanding the universe in ever greater depth from right where we are. The stars may be forever out of reach for our physical selves, but they are not out of reach for our curiosity, our intellect, and our relentless drive to know. That is a journey with no speed limit. So, if our physical journey to the stars is redefined by that ultimate speed limit, then the next thing we have to truly wrap our heads around is the stage upon which this drama plays out, the distances involved. And here's the brutal truth. Our brains are utterly unequipped to understand them. We evolved to judge the distance to a water source, the reach of a thrown spear, the horizon from a hill. Our entire intuitive sense of scale is planetary. We think 1,000 kilometers is a long trip, and a flight across an ocean feels like a major undertaking. But space operates on a different plane entirely. To even begin talking about travel between stars, we have to abandon every instinct we have about what is near and what is far. The first mental shift is to stop thinking in kilometers or miles. Those units become comically useless, like measuring a continent with a fingernail. The only sensible unit is the light year. Now, we casually throw that term around in sci-fi, but its reality is mind-numbing. A light year is the distance a beam of light travels in one Earth year. Light, the fastest thing in the universe, moving at that impossible speed of 300,000 kilometers per second for an entire year. When you do the math, that comes out to roughly 9.5 trillion kilometers. That's a 9 followed by 12 zeros. To put that in some pathetic earthly perspective, if you could drive a car at a constant 100 kilometers per hour 24/7, it would take you over 10 million years to cover a single light year. The nearest star system to our own, Alpha Centauri, which includes Proxima Centauri, is about 4.24 light years away. That's the target right next door. That's our cosmic backyard neighbour. 100 kilometers per hour 24/7, it would take you over 10 million years to cover a single light year. The nearest star system to our own, Alpha Centauri, which includes Proxima Centauri, is about 4.24 light years away. That's the target right next door. That's our cosmic backyard neighbour. To get there, light itself, the ultimate speedster, takes over 4 years. Our fastest human-made objects, the Voyager probes, are chugging along at about 60,000 kilometers per hour. At that pace, it would take Voyager 1 over 70,000 years to reach Proxima Centauri. It's already been travelling for nearly 50 years and has barely left the solar neighbourhood. This is the first gut punch of cosmic scale. The very closest thing to us is still hopelessly, absurdly far. And this is where the illusion of proximity completely shatters. When you look up at the night sky and see those pinpricks of light, they're not just far away, they're asterisk, historically asterisk, far away. It passed. Now, let's scale up. Our home galaxy, the Milky Way, is a vast spiral disk of stars, gas and dust. Its diameter is about 100,000 light years. That means a signal of light travelling at the universal speed limit would take 100,000 years to go from one edge to the other. For a spacecraft, even a hypothetical one travelling at a significant fraction of light speed, say 10%, that's a journey of 1 million years. The galaxy isn't just big, it is temporally enormous. A crossing isn't a voyage, it's a geological epoch, and our Sun is just one of perhaps 200 billion stars in this disk, most of them spaced many light years apart. This is the rule, not the exception. Our solar system feels crowded with planets, but the space between stars is almost incomprehensibly vacant. If you shrunk the Sun down to the size of a grain of sand, on that scale the next grain of sand, Proxima Centauri, would be over 4 miles away. The space in between is just that, empty space. This void is what any interstellar traveller must cross, a desert of nothingness lasting for years. But the real kicker comes when we zoom out to the observable universe. Galaxies themselves are the new islands. The Andromeda Galaxy, our closest large galactic neighbour, is 2.5 million light-years away. Our entire local group of galaxies fits within a span of about 10 million light-years, and the observable universe, the sphere of all we can possibly see because light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years, giving it a diameter of over 93 billion light-years. This number is larger than the age of the universe because of the expansion of space itself, but that's another story. The point is, against this backdrop, the 4 light-years to Proxima Centauri seem trivial, but that's the ultimate illusion. They are not trivial to us, the creatures bound by physics and time. They're an unbridgeable gulf on human timescales. This scale transforms the very concept of exploration. On Earth, exploration meant going over the horizon, maybe being gone for a few years and returning with tales and maps. In interstellar space, a probe sent to a nearby star would not send back a signal for over 4 years, and its reply would take another 4 years to return. The people who launched it might be retired or deceased by the time the first postcard arrives. For destinations hundreds or thousands of light years away, the mission becomes a legacy for descendants you will never meet. The communication delay alone makes any real-time control or interaction impossible. It forces a complete redefinition of a mission. Is not an expedition, is a message in a bottle cast into a cosmic ocean, with the faint hope that someone, millennia hence, might be around to catch the reply. This distance also has a direct, crushing impact on propulsion. The tyranny of the rocket equation, which already makes spaceflight harder in our solar system, becomes a monster. To carry enough fuel to accelerate a payload to even a modest fraction of light speed, then maybe slow down at the destination, requires an amount of propellant that grows exponentially with the desired speed. For a realistic crewed ship, the fuel mass would be many times that of the ship itself, and that fuel itself needs to be accelerated, creating a vicious cycle. Concepts like nuclear pulse propulsion or fusion rockets might theoretically get us to maybe 10% of light speed after years of acceleration, but that still means a 40-year journey to Alpha Centauri. And that's one way. Sending humans on a one-way, multi-decade journey through a vacuum filled with cosmic rays and micrometeoroids is a biological and psychological challenge we have no answer for. So the distance doesn't just make the trip long, it amplifies every other technical problem by orders of magnitude. Radiation shielding has to last for decades without fail. Food, water and air must be perfectly recycled or grown for generations. Social structures must remain stable in a confined, isolated can for longer than most civilizations last. The distance is the quiet, imposing judge that declares most of our ideas infeasible. It's why so much thought goes into alternative, non-chemical propulsion. Ideas like solar sails pushed by powerful lasers from Earth, or antimatter engines, or even more speculative concepts. But even these, if they ever become real, are merely ways to inch our way across the gulf a bit faster. They don't shrink the gulf itself. And this brings us to a crucial, often overlooked point. The galaxy is not static. While the distances between stars within a galaxy are relatively stable over human timescales, the universe itself is expanding on larger scales. This means that for galaxies beyond our local group, they're moving away from us at speeds that increase with distance. Eventually, for galaxies far enough away, their recession velocity due to the expansion of space exceeds the speed of light. This doesn't violate relativity because it's space itself stretching, but it means those galaxies are forever beyond our reach, even in principle, if we are bound by the speed of light. Their light can reach us, but we can never reach them, so not only are distances vast, but for a significant portion of the universe, they're growing. The cosmic horizon is slowly shrinking in terms of accessibility. Our window of opportunity to physically reach certain regions, if we ever could, is not infinite. This expansion adds another layer of profound isolation. It means we're not just on an island in space, but, in a sense, in an island in time. Our cosmic neighbourhood, the collection of galaxies gravitationally bound to us, is our only possible physical realm. Everything else is receding into a permanent, unreachable twilight. So what does this immense scale mean for the future? It strongly suggests that human expansion, if it happens, will be slow, patient, and incredibly local by galactic standards. We might settle the solar system, perhaps even figure out how to travel to a handful of the very closest stars over millennia. But a galactic empire, with ships buzzing between stars like airplanes between continents, is almost certainly a fantasy born of our planetary scale intuition. It's more likely that intelligent life, if it exists elsewhere, is similarly constrained. The galaxy may be full of life, but isolated in pockets so distant that communication takes centuries and travel takes eons. This scale might be the great filter, not a destructive one, but a logistical one that prevents civilizations from ever meeting face to face. Our exploration will therefore likely continue to be done with telescopes and robotic probes. We will explore by collecting photons and analysing spectra. We will build bigger and better eyes to peer across the light years and learn about exoplanets, but we will probably never set foot on them. This isn't a pessimistic view, it's a realistic one based on the numbers. It shifts the goal from planting flags to gathering knowledge. The journey becomes intellectual, not physical. The vast distances are not a challenge to be overcome with bigger engines. They're a fundamental condition of our existence in the cosmos. They define the arena we play in, and in doing so, they force a kind of cosmic humility. We are not the lords of creation, destined to spread across the galaxy. We are a curious, fragile species on a tiny rock, gifted with the ability to see and wonder at the incredible vastness that surrounds us, but perhaps never to touch it. And in a strange way, that might be okay. Understanding our true place, our actual scale in the universe, is one of the greatest achievements of science. It grounds our ambitions in reality. It tells us to cherish our pale blue dot, to solve our problems here, because this is very likely the only home we will ever have. And as we look out at those unimaginable distances, we can still send our machines, our messages, and our thoughts. We can still connect, not through travel, but through understanding. The universe is under no obligation to be accessible to us. The fact that we can comprehend its scale at all is a triumph. All that talk about scale leads to the next equally brutal question: how do you pay for the trip? We've established the universe is unimaginably vast, and the speed of light is an unbreakable rule. But even if we aim for a respectable fraction of that speed, say 10 or 20%, the universe presents us with a bill. And it's not a bill in dollars or euros, it's a bill in energy. Pure, raw, physical energy. This is where the dream of interstellar travel collides with the unforgiving mathematics of physics, and the numbers that come out are enough to make any engineer weep. It's not just that we need a lot of energy, we need an amount that grows in a way that feels like a cruel joke as you go faster. This is the heart of the problem. Let's start with a concept every rocket scientist knows and fears: the tyranny of the rocket equation. This isn't about relativity yet, this is basic Newtonian physics. To go faster, you throw stuff out the back of your rocket. That stuff is propellant, or reaction mass. The problem is, you have to carry all that propellant with you from the start. As you add more propellant to go faster or farther, you increase the total mass of the ship, which means you need even more propellant to push that heavier mass. It's a vicious exponential cycle. For a simple rocket to reach a high final speed, the mass of propellant needed can be hundreds or thousands of times greater than the mass of the actual payload you want to deliver. This is why our chemical rockets are giant fuel tanks with a tiny capsule on top. Now take this already nasty problem and apply it to an interstellar journey. To get to another star in a human lifetime, you need tremendous speed. Chemical rockets, the kind that took us to the moon, are pathetically inadequate. Their exhaust velocity is simply too slow. It's like trying to cross an ocean in a rowboat. You can't carry enough food and water for the trip. The most efficient chemical engines we have would require a fuel mass larger than the visible universe to reach a nearby star in a reasonable time. So we have to look at more powerful, theoretical propulsion. This is where the energy demand becomes cosmic. One promising idea is nuclear fusion. Imagine a rocket that works like a controlled hydrogen bomb, fusing light elements into heavier ones and blasting the superheated plasma out the back. The exhaust velocity would be much, much higher than chemical engines. In theory, a fusion rocket could get us to maybe 10% of light speed after a long acceleration period. But the energy required is still staggering. You need to first achieve sustained fusion, a problem we haven't solved on Earth for power plants, let alone in a compact, reliable rocket engine. Then you need to carry the fusion fuel like deuterium and helium-3. Estimates suggest that for a modestly sized crewed ship to reach Alpha Centauri in, say, 50 years, you might need thousands of tons of fuel. The mining and processing of that fuel, especially something rare like helium-3 which might be harvested from the moon or gas giants, becomes a mega engineering project spanning the solar system, and we're still just talking about 10% of light speed. Now let's crank it up. What about 90% of light speed? Or 99%? This is where Einstein's relativity comes back with a vengeance. As an object with mass accelerates closer to the speed of light, its relativistic mass increases. From the perspective of an outside observer, it gets heavier and heavier. This means the energy needed for each additional increment of speed grows asymptotically, approaching infinity at the speed of light. The relationship is not linear, it's a steep, punishing curve. To accelerate a single ton of mass to 90% of light speed requires energy equivalent to millions of tons of matter, converted perfectly to energy via Einstein's famous equation E equals mc squared. That's the total energy yield of hundreds of thermonuclear weapons, all directed perfectly into pushing that 1 ton. For a ship big enough to carry humans and their life support, which would weigh thousands or tens of thousands of tons, the energy requirement becomes comparable to the total energy output of our entire civilization for centuries. Some calculations suggest it could exceed the total solar energy falling on Earth for a year. We're talking about harnessing the power of a star. This leads to the most extreme and theoretically most efficient concept, matter-antimatter propulsion. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, mostly in the form of intense gamma rays. If you could direct that energy into an exhaust, you'd have the ultimate rocket engine. The exhaust velocity could be a significant fraction of light speed. The problem, aside from the unimaginable engineering of containing and directing such energies, is production and storage. We currently produce antimatter, like positrons or antiprotons in particle accelerators. The amounts are minuscule, measured in atoms. The cost to produce a single gram is astronomical, requiring the energy output of massive power plants for years. To fuel an interstellar ship, you might need tons of the stuff. Storing it is another nightmare, as it must be perfectly isolated from all normal matter using complex magnetic traps. Any failure means a catastrophic explosion. So while matter-antimatter represents the pinnacle of energy density in physics, actually creating and managing the fuel for a trip is far beyond any technology we can envision, making it a concept for the far, far future if ever. Given these monstrous energy demands, some thinkers propose leaving the fuel at home. This is the idea behind beamed propulsion. Instead of carrying your energy source, you have a stationary power plant, like a massive laser or microwave array stationed in the solar system, perhaps orbiting the sun. This array beams power to a spacecraft equipped with a giant sail. The momentum of the photons in the beam pushes on the sail, accelerating the craft. Since the power source stays home, the spacecraft can be very light, just the sail, a tiny payload, and maybe a small power source for communications. This cleverly sidesteps the rocket equation's tyranny. We could potentially accelerate very small robotic probes to 20 or 30% of light speed using technology we can almost imagine today, like a terawatt-scale laser array. But even this has staggering energy needs. Powering that laser for the years required to accelerate the probe would consume a significant portion of our planet's energy output. And then there's the problem of stopping. The beam can push you out of the solar system, but how do you slow down at the destination? You'd need a mirror to reflect the beam back at you, or a separate laser array at the target star, which obviously isn't there. Or you carry a small rocket for deceleration, which brings back the fuel problem. For crewed ships, beam propulsion faces even bigger hurdles, as a sail large and sturdy enough to carry a human habitat would be an engineering marvel and would still require mind-boggling power to push. So let's think about this energy problem from a different angle. Is there a cheat? Some people point to time dilation as a way to reduce the energy needed. The idea is that if the crew experiences less time due to relativistic effects, maybe they can travel a long distance with less life support and thus a smaller, more energy-efficient ship. But this is a misunderstanding. Time dilation doesn't reduce the energy required from the perspective of the launch civilization. In fact, to achieve the high speeds that cause significant time dilation, you need even more energy. The savings in life support mass for the crew is utterly trivial compared to the exponential energy cost of reaching that speed in the first place. The energy bill is paid by the people who stay behind, and it's a fixed enormous cost based on the final velocity and mass of the ship, not the subjective time experienced on board. This leads to the ultimate, sobering conclusion about energy. The cost of a single crewed interstellar mission using any plausible technology we can conceive of, would represent a significant fraction of a civilization's total economic and industrial output for generations. It would be a project on the scale of building a Dyson sphere, not a spacecraft. It forces a harsh prioritization. Would any society choose to divert that much resource, that much focus, away from solving problems on its home planet, to send a handful of people on a one-way journey to another star? The energy barrier is thus not just technical, it's socio-political and economic. It asks what we value as a species. The energy challenge also clarifies why robotic probes are the only realistic near to medium term option. They can be smaller, lighter, and don't need a return ticket. We can contemplate a slow, patient exploration with tiny sails pushed by lasers, accepting travel times of centuries. The energy cost, while still huge, becomes at least theoretically manageable for a determined global civilization. It becomes a long-term scientific investment, like building a cathedral rather than an all-out sprint. So, when we look at the stars and dream of visiting them, we must remember that the price of speed is not linear, it's exponential. Each decimal point closer to light speed comes with a cost that multiplies. Our current civilization is like a child who has just learned to make a campfire, gazing at a mountain range and wondering about the logistics of moving those mountains. We have glimpsed the physics of the journey, and in doing so we have seen the price tag. And that price tag tells us that the path to the stars is not one of sudden, explosive expansion, but of slow, patient, and incredibly efficient mastery of energy itself. It may be that becoming an interstellar species is less about building a great ship and more about learning to harness the power of a star. Until we can do that, the stars will remain forever in our sight, but forever out of our reach. This energy barrier is perhaps the most concrete, calculable limit we face, a number written into the laws of physics that we cannot wish away. It demands not just better engines, but a fundamental transformation in how we power our civilization. So, you've somehow solved the energy problem. You've built a ship with a miraculous engine that can push you to a significant fraction of light speed. You've paid the cosmic energy bill, but as you accelerate, you'll receive another surprising invoice, and this one is paid in time itself. Not just the years that pass, but the very flow of time becomes relative, creating a paradox that is as fascinating as it is isolating. This is the realm of time dilation, a direct prediction of Einstein's special relativity, and it transforms a long journey into a profoundly strange one. The basic rule is this: the faster you move through space relative to someone else, the slower your time moves relative to theirs. It's not a mechanical error or a perception trick. It's a fundamental feature of the universe, verified countless times with ultra-precise atomic clocks on fast-moving airplanes and satellites. For interstellar travel, this effect stops being a tiny curiosity and becomes the central fact of the mission. Let's say you board a ship destined for a star 100 light-years away. From the perspective of everyone on Earth, if your ship travels at an impossible 99.9% of light speed, the journey will take just over 100 years. A century will pass back home. But for you, on the ship, because you're moving so fast, time is passing much more slowly. Your clocks tick slower, your heart beats slower, your entire biological process slows down relative to Earth. For that same journey, you might only experience perhaps 4 or 5 years. You could, in theory, travel across 1,000 light-years of the galaxy within a single human lifetime. From your point of view, this is the so-called Starship as Time Machine effect. It seems like a fantastic bonus, a cosmic loophole. The galaxy opens up, you can go anywhere. But here's the catch, and it's a devastating one. This loophole only works for the travellers. Everyone and everything you ever knew is left behind in the normal flow of time. When you turn around and come back, or even just send a message home, you're confronting that accumulated time debt. Let's make this painfully concrete with the classic twin paradox. One twin stays on Earth, the other twin gets on a starship and goes to a star 10 light-years away at 80% of light speed. For the Earth twin, the calculation is simple. 20 light-years total distance there and back, divided by 0.8 light speed, equals 25 years of travel time. She waits 25 years for her sibling to return. For the travelling twin, due to time dilation, only 15 years pass. He returns biologically 15 years older to find his earthbound sister who has aged 25 years. He has, in a very real sense, jumped 10 years into her future. Now scale this up. Make it a journey of a few hundred light years at 99% of light speed. The crew might experience a couple of decades. They return to an Earth where 10 generations have passed. The language has evolved. The political borders, the culture, the technology, everything is unrecognisable. Their mission report their very existence as an archaeological curiosity. They are living fossils from a distant past. Their bank accounts, their social connections, their purpose for going, all of it is gone, rendered irrelevant by the passage of centuries back home. This is the ultimate loneliness. You haven't just travelled through space, you've been exiled in time. This has immediate crushing consequences for the idea of interstellar exploration as a human endeavour. First, it makes any notion of a mission in the traditional sense absurd. You're not exploring for the people who sent you. They will be dust long before your first data packet arrives. You're exploring for their distant descendants, who may not even know or care about your mission. The link between the motivation for the journey and its outcome is severed by time. Second, communication becomes meaningless as a conversation. You can send a message, but the reply will come back to a ship that may have moved on, or to your great-grandchildren born on the ship. Real-time dialogue with Earth is impossible. Your only ongoing conversation will be with the ship's computer and your fellow crewmates, trapped in the same time bubble. Third, it turns any round trip into a one-way trip for your social and cultural existence. You can never go home again, because home is a period in history, not just a location. This psychological burden is immense. Could a crew truly consent to knowing they are giving up not just their own connection to their era, but also the possibility of any future connection for all their descendants born en route? This leads to the dark side of the generation ship concept in a relativistic context. If your ship is not going fast enough to experience severe time dilation, then it's a multi-generational arc, and the society aboard evolves on a timescale not too different from Earth's. But if you're going at relativistic speeds, the people on the ship experience time slowly. From their perspective, the journey between stars might be a single generation's work, but from Earth's perspective, it still takes centuries. So, if a generation ship bound for a star 200 light away travels at a modest 10% of light speed, Earth sees a 2,000-year journey. The ship might host 80 generations. But if that same ship could travel at 99% of light speed, Earth sees a 202-year journey, but the crew might only experience 28 years. This creates a bizarre scenario. For the high-speed ship, there is no need for multiple generations. The original crew arrives. But they arrive in a future so distant that the Earth that launched them is ancient history. Which version is more tragic? The society that slowly forgets its purpose over 80 generations in a tin can, or the crew that stays young but loses their entire world in what feels like a few decades? Time dilation doesn't solve the human problem, it morphs it. It also introduces a severe navigation and planning challenge. The star systems you are aiming for are not static. Over the centuries that pass in the galaxy's frame of reference, stars move. The orbits around the galactic centre mean their positions change. Your ship's computer, using data centuries old from launch, would have to project where the target star will actually be when you arrive, making mid-course corrections based on predictions, not direct observation. You're essentially throwing a dart at a moving target from a moving platform with a several-century delay in your vision. Furthermore, the physics of acceleration and deceleration adds another layer. To get up to these fantastic speeds and then slow down at your destination, you need to accelerate for years, maybe decades, then flip and decelerate for the same amount of time. The time dilation effect is most pronounced during these high-speed cruise phases, but the entire journey profile is affected. The crew doesn't just jump into a time bubble, they gradually enter and exit it. This complicates the simple twin paradox math, but the core conclusion remains: the travellers experience less time. So is there any upside for humanity at large? Perhaps a probe. A robotic scout travelling at relativistic speeds could send back data. But even then, the time dilation works against the waiting scientists. Let's say we launch a probe to a star 500 light-years away at 90% of light speed. From Earth's view, the probe takes about 555 years to get there. It then takes another 500 years for its first radio signals to travel back. Scientists on Earth get their first data over 1,000 years after launch. The project becomes a monument, not a research paper. For the probe itself, if it had a clock, only about 240 years would have passed from its launch to its arrival at the star. But this is irrelevant. It's a machine. This starkly highlights that time dilation is a benefit only for the travelling object, not for the network it leaves behind. It allows a physical object to traverse the galaxy, but it severs that object from the temporal context of its origin. In the end, time dilation presents us with a cruel choice. To make the galaxy traversable within a human lifespan, you must forfeit your place in human history. You can have the adventure, but you must give up the home you are adventuring for. It frames interstellar travel not as an extension of human society, but as an irrevocable divorce from it. The travellers become ghosts, moving slowly through time while the universe buzzes past them at a normal pace. They are time travellers headed only one way, into the future, at a rate they cannot control. This isn't a barrier of engineering or energy, it's a barrier of meaning and connection. Why go, if those you go for will never know you succeeded? Why send humans when they will become disconnected artifacts? The physics gives us a way to cheat the clock, but in doing so, it reveals that the clock was never the real problem. The real problem is our desire to remain part of a collective story, a timeline. Time dilation allows you to win the race against your own mortality, but only by losing the race against everyone else's. It saves your life, but at the cost of your world. So, while the mathematics of relativity offers a path across the light years, the human consequences of that mathematics suggest that the path is one of profound, perhaps unacceptable, solitude. The universe may permit the journey, but it ensures the traveller can never truly return. The social and ethical structures around raising children in a closed, mission-critical environment are unexplored and fraught with peril. In essence, every human need becomes an engineering crisis of the highest order. We need air, water, food, gravity, radiation shielding, medical care, mental stimulation, social stability, and reproductive continuity. Meeting any one of these needs for a century in deep space is a monumental challenge. Meeting all of them simultaneously in a single vehicle that also has to propel itself across light years borders on the impossible. This is why, when you look at the problem coldly, the human body appears to be the weakest link in the interstellar travel chain. It is the component most likely to fail, with the most demanding and non-negotiable requirements. This biological fragility is the strongest argument for robotic exploration. A probe doesn't get osteoporosis, doesn't get lonely or stage a mutiny. It can be hardened against radiation far more easily than tissue. It can wait patiently in silence for decades. It doesn't need a closed ecosystem. When we dream of touching the stars, we imagine doing it in person. But the stars may be a destination only for our minds and our machines, while our bodies, this beautiful and intricate product of Earth, remain forever tethered to the planetary environment that shaped us. The final barrier to the stars may not be out there in the physics of space-time, but right here, in the very blood and bone and mind that makes us want to go in the first place. Given all the ways a human body fails in space, the logical workaround for a multi-century journey is to stop relying on a single crew. You send a community instead, one that will sustain itself, reproduce, and carry the mission forward across generations. This is the generation ship concept, a self-contained world travelling through the void where the original crew's great-great-great-grandchildren are the ones who finally arrive. It transforms the mission from a voyage of exploration into a mobile miniature civilization. But solving the biological durability problem this way introduces a whole new universe of sociological, ecological, and existential challenges that are, in many ways, even more daunting than the physics. First, consider the ship itself. It is no longer a vessel, it is an ark. It must be enormous, a sealed ecosystem capable of supporting hundreds, perhaps thousands of people for centuries without any resupply. We are not talking about a beefed-up International Space Station. We are talking about something closer to a hollowed-out asteroid, or a gigantic cylindrical world rotating to provide artificial gravity. Inside, you need to replicate all the fundamental systems of a planet: atmosphere revitalization, water purification, waste recycling, and food production. This means vast agricultural modules, forest fields and aquaculture tanks under artificial suns. The entire loop of life must be perfectly balanced. A single crop blight, a build-up of a toxic compound in the water cycle, or a failure in the bacterial communities that process waste could cascade into a disaster. The ship's biosphere would be terrifyingly fragile, with no buffer, no vast oceans or atmosphere to dilute mistakes. It would require constant, vigilant management by generations of ecologist engineers who must maintain knowledge that hasn't been needed for millennia on Earth. This isn't just engineering, it's a perpetual tightrope walk over an abyss. Then there is the human society inside this tin can. The founders launch with a shared purpose to reach the new world. But what about their children? Born into the metal corridors of you who know nothing but the ship. The ship is their entire universe. The mission to a distant star is a story, a legend, a piece of history. Their immediate concerns will be about their lives ** now, *. Jobs, social status, relationships, resources. Within a few generations, the original mission could become a background myth, a vague religious or cultural mandate, while the day-to-day politics of the ship take centre stage. Could you maintain a unified, focused society for hundreds of years when the primary goal is dozens of generations away? History suggests not. Factions would arise. Disputes over resources, leadership, and the very direction of the ship would be inevitable. What if a majority decides a century in that they want to turn back, or stop accelerating, or change course to a different star? The mission's continuity depends entirely on social stability, something humans have never been great at over such timescales, even on a planet. The ship would need a governance system robust enough to prevent civil war, flexible enough to adapt over centuries, and just enough to prevent a disgruntled faction from sabotaging the life support. We have no model for this. Population control becomes a critical and ethically fraught necessity. The ship has a strict carrying capacity. You cannot have unchecked population growth. This means strict rules about reproduction, licenses, quotas, perhaps a one-child policy. Who decides? How are these rules enforced? What happens to those who break them? The social tensions from such control would be immense. Conversely, you also need a minimum viable population to avoid genetic bottlenecking and inbreeding depression over centuries. Geneticists estimate you'd need at least several hundred, likely several thousand, genetically diverse individuals at the start to maintain a healthy gene pool. Even then, you'd need careful matchmaking over generations, managed by computers, to ensure genetic health. This is a level of societal control over personal life that is unprecedented. The culture aboard would inevitably drift, and then radically transform from Earth culture. Isolated for centuries, with a unique environment and history, they would develop their own language, accents, slang and idioms. Their art, music and stories would reflect their reality. The endless corridors, the artificial sky, the recycled air. They might develop a religion venerating the founders or the destination. They would have no concept of seasons, oceans, mountains, or any of the natural phenomena that shaped Earth's cultures. Their frame of reference would be entirely technological and enclosed. By the time they arrive, they might be utterly unrecognisable to any Earthlings who might later receive their signal. This leads to the most profound question of all. Who is this mission for? The founders launched it for humanity's future, to spread life to another star, but the arrivals are not the founders. They are people born in transit for whom the ship is home. The target planet, no matter how Earth-like, will be a hostile, alien environment requiring a massive colonisation effort. Why would they leave the only home they've ever known, a perfectly tuned, climate-controlled world, for a dangerous, uncertain planetary existence? The mission could fail at the very moment of success because the descendants have no desire to land. The ship itself is their world. The destination is just a strange place outside the airlock. So the mission architecture would have to somehow instill a burning desire for planetary life in generations who have never seen a planet. Their education, their stories, their very identity would have to be tied to a place they have never experienced. It's a profound psychological engineering challenge. Technologically, the ship must be immortal. Every system, from the smallest air filter to the massive hull plating and propulsion drive, must either last for centuries or be repairable and replaceable, using only the resources and manufacturing capabilities on board. This implies a fully functional industrial base inside the ship, mining and refining from stored raw materials or asteroid debris collected en route, fabrication plants, electronics manufacturing. You need to maintain the knowledge to do all of this, passing down not just theory but hands-on, practical engineering skills for systems the apprentices have never seen fail. The ship's library, both digital and perhaps physical, becomes its most sacred treasure. Data corruption or loss could be catastrophic. There's also the psychological impact of the sky. In a rotating ship, the ground would curve upward, and the sky would be the far side of the hull. Would this feel open or claustrophobic? Studies in closed environments suggest that even simulated views of nature are crucial for mental health. Would they have massive screens showing Earth landscapes? Or would that just breed nostalgia for a place they can never visit? The environment would be fundamentally unnatural, and we have no idea what the cognitive effect of growing up in such a place would be over 20 generations. Furthermore, the ship is vulnerable to a single unstoppable disaster, a major micrometeoroid impact, a critical system failure that cascades, or a social collapse that leads to sabotage could end everything. There is no rescue, no plan B. The investment is total. This raises a final ethical point. Is it right to create generations of people who have no choice but to live and die in a metal tube, all for a goal set by their ancestors? They are born into a life of permanent confinement with a pre-assigned purpose. Do they have the right to change that purpose? The generation ship concept, initially seeming like a neat solution to the lifespan problem, actually opens up a deeper box of puzzles. It forces us to realise that a journey that long ceases to be a journey in any normal sense. It becomes a migration, a societal experiment of the most extreme kind. The focus shifts from astrophysics and propulsion to ecology, sociology and psychology. The question is no longer, can we build a ship fast enough? But can we build a society stable enough? And can we build a world complete enough? We have never created a perfectly self-sustaining ecosystem on Earth, let alone in space. We have never maintained a peaceful single-purpose society for centuries. In many ways, building the society might be harder than building the engine. The generation ship is therefore a mirror. It shows us that the greatest barriers to interstellar travel might not be out there, among the stars, but in here, in our understanding of how communities work, how cultures evolve, and how fragile the balance of a closed biosphere truly is. It suggests that a species capable of successfully sending a generation ship is a species that has already mastered sustainability, social harmony, and long-term thinking on a scale we can barely imagine. In that light, the journey itself becomes the test. If you can survive centuries in a sealed can, you might just be ready to colonize a new world. But if you can't, you'll never get the chance to try. Even if humanity masters the generation ship, achieving a stable society that can endure the millennia, and even if we solve the physics of propulsion to cross the vast distances between stars within our galaxy, there is a larger, more insidious barrier at work on the grandest scale. The universe itself is not static, it is stretching, and this expansion is not just a background fact, it actively shapes what is possible, placing a horizon around our ambitions. This is the discovery of Edwin Hubble from about a century ago, refined dramatically in the last few decades. The universe is expanding, and that expansion is accelerating. This means galaxies are not simply moving apart through space. The very fabric of space between them is growing. Think of dots on the surface of an inflating balloon. As the balloon expands, each dot sees every other dot moving away, with dots further away receding faster. Now apply that to the cosmos. A galaxy 10 million light-years away is moving away from us slower than a galaxy 100 million light-years away, and a galaxy far enough away is being carried off by the stretching of space at a velocity that exceeds the speed of light. This does not violate Einstein's rule that nothing can travel through space faster than light. The galaxy itself isn't moving through space at that speed. The space between us and it is expanding, creating the effect of recession. This distinction is crucial. It leads to the concept of the cosmological horizon, also called the Hubble horizon. Beyond a certain distance, the expansion velocity surpasses the speed of light. Anything beyond that point is causally disconnected from us. Its light travelling toward us is fighting against the expansion of space itself. For regions sufficiently far, the light will never reach us, and we will never reach them, even if we left today at light speed. We are in a bubble of the observable universe, and that bubble's boundary is defined by this expansion. The radius of this observable sphere is about 46 billion light-years, but the key point is that as time goes on and acceleration continues, This bubble of what we can asterisk see asterisk actually grows, but the bubble of what we can ever asterisk reach asterisk shrinks. More and more galaxies will cross that light speed recession threshold and fade from our future potential. They become islands forever receding into the darkness. For interstellar travel, this adds a tragic philosophical layer to the already immense challenge of distance. It's not just that stars are far apart. For a significant portion of the universe, the very gap between us and them is widening at an ever-increasing rate. Let's bring this home to our galactic neighbourhood. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 50 other smaller galaxies, is gravitationally bound. The mutual gravity within this group is strong enough to overcome the expansion of space on these relatively small scales. So Andromeda is actually moving asterisk toward asteriskus, on a collision course billions of years in the future. All the stars within our own galaxy are held together by gravity. So, for travel within the Milky Way or to Andromeda, cosmic expansion is not a direct factor. The barrier here is the sheer galactic distance and the light speed limit, not expansion. However, for any dream of travelling beyond our local group, to other clusters of galaxies, expansion becomes the dominant, unbeatable foe. Imagine aiming for a galaxy in the Virgo cluster, about 54 million light-years away. Even at the impossible speed of light, the journey would take 54 million years from our perspective. But during those 54 million years, the universe continues to expand. The destination galaxy is not sitting still. It is being carried away. By the time you arrive, if you ever could, the galaxy would be much farther away than when you started. Your trip would be like running up a down escalator that is steadily increasing its speed. For truly distant targets, the escalator speeds up so much that you make no progress relative to your destination, despite moving at light speed through the space immediately around you. This reality means that the universe, in its current accelerated state, is essentially telling us that certain chapters of the cosmic story are already closed to us. We will never visit, or even send a probe to, the spectacular galaxies we see in deep-field telescope images. They are visual histories, not future destinations. Their light reaches us as a postcard from the past, but we can never send a reply. This transforms the goal of interstellar travel from a "when we have the technology" dream into a "the window is closing" scenario. The universe in its early epochs was smaller and denser, and expansion was slower. Billions of years ago, galaxies were closer together. A civilization emerging then would have had, in principle, a larger reachable cosmos. Today, that reachable cosmos is smaller, and in the far future, it will be smaller still. For a civilization that arises tens of billions of years from now, the universe outside its immediate gravitational cluster will be so vastly expanded that all other galaxies will have redshifted out of sight, their light too faint and stretched to detect. The night sky for their astronomers will be dark and empty, save for the stars in their own dying galaxy. They will have no evidence of a larger universe, no cosmic context. In that sense, we live in a privileged time, cosmically speaking, where we can still see the evidence of the Big Bang and map a vast universe. But that privilege does not extend to physical access. This expansion is driven by something we call dark energy, a mysterious form of energy inherent to space itself. As space expands, more space is created, and with it more dark energy, causing the expansion to accelerate. We do not know what dark energy is, but its effect is measurable and dominant. It constitutes about 68% of the total energy content of the universe. This means the fate of the cosmos is not to coast apart slowly, but to be ripped apart at an ever-quickening pace. On the largest scales, gravity, the force that pulls things together, loses the war to dark energy, which pushes things apart. For the practical engineer considering interstellar travel, this might seem like an abstract, long-term issue, but it frames the ultimate futility of certain ambitions. It places a hard, physical limit on the scope of any future galactic or intergalactic civilization. That civilization could flourish for billions of years within its own galaxy, but it could never build bridges to other galaxy clusters. Each cluster becomes an isolated island universe, forever separated by an ever-widening ocean of nothingness. This has profound implications for the search for extraterrestrial intelligence and the famous Fermi paradox, which asks, where is everybody? One possible answer is that space is just too big, and now we have to add, and it's getting bigger, faster. Even if intelligent life is common, it may be forever locked into its own island of stars, unable to traverse the growing voids between galaxies. The Great Silence might not be because life is rare, but because the cosmos is structured to keep civilizations apart, a cosmic quarantine enforced by the geometry of space-time itself. So, when we consider the project of interstellar travel, we must add this cosmological caveat. Our reach is limited not just by our technology and biology, but by the fundamental dynamics of the universe. The Milky Way is our home, and it is likely the only home our species will ever physically know. The 100,000 light-year diameter of our galaxy is not just a measure of size, it is the boundary of our potential empire. Beyond it lies an abyss that is not merely empty, but actively expanding, pushing other islands of stars away from us at speeds we can never match. This realization can feel like a prison sentence, but it can also reframe our mission. It makes our galactic neighborhood infinitely more precious. It turns our focus inward, to understanding and cherishing the stars we can actually reach. The thousands of exoplanet systems within our own galaxy are not just practice runs, they are the only realistic targets we will ever have. The expansion of the universe, therefore, is the ultimate unbeatable barrier. It is not a wall we can break through with a better engine. It is the stage itself changing its shape, ensuring that the most dramatic acts of the cosmic play happen in isolated theatres, with no audience from other theatres ever able to attend. We're in one such theatre. Our journey, if it is to happen, will be a local one. The grand galaxy-hopping narrative of science fiction is, according to our best physics, a fantasy. The universe is not just big, it is fleeing from us. And in that flight, it sets the final, unchangeable limits on the dream of the stars. Passive shielding, like thick slabs of metal or water, quickly becomes impractical due to mass. Remember, every kilogram of shield must be accelerated. A shield thick enough to reliably stop a 1-gram grain at relativistic speeds might need to be meters or even tens of meters of solid material, making the ship impossibly heavy. Some theoretical designs propose a Whipple shield or multi-layer system where an initial thin bumper vaporizes the impacting particle, spreading its energy out, which is then absorbed by a secondary shield. But at these energies, even a vaporized particle turns into a plasma fireball that can still catastrophically damage the next layer. Other ideas involve active shielding. The most discussed concept is a magnetic or plasma shield. The idea is to project a powerful magnetic field ahead of the ship, strong enough to deflect the electrically charged protons and ions. Since most of the interstellar atoms are ionized or can be ionized by a laser, this could theoretically sweep them aside. However, this does nothing for neutral atoms or dust grains, which would pass right through the magnetic field. You would need a complementary system, perhaps a powerful laser array, to vaporize and ionize incoming dust before it hits, turning it into a plasma that the magnetic field can then deflect. The engineering and power requirements for such a system are, once again, astronomical. You need to detect incoming micrometeoroids at great distances, track them, and zap them with precision, all while moving at a significant fraction of light speed. The power needed to sustain both the magnetic field and the defensive laser system would be a major fraction of the ship's total propulsion power. Then there is the constant sandblasting effect of the atomic hydrogen itself. Even if each impact is tiny, the cumulative effect over years or decades of travel is significant erosion of the forward hull. Think of it as a form of relativistic weathering. The leading edges of the ship would be slowly worn away atom by atom. This is a serious concern for any exposed instrumentation, sensors or communications arrays pointed in the direction of travel. They would need to be heavily armoured or retracted behind shields during the high-speed cruise phase, which complicates navigation and science. This hazard also dictates your route. You cannot just plot a straight line through the galaxy. You must map and avoid regions of higher density in the interstellar medium. Nebulae, beautiful clouds of gas and dust in telescope images, become deadly zones of high resistance. A molecular cloud, where densities can be thousands or millions of atoms per cubic centimetre, would be utterly impassable at relativistic speeds. The constant impacts would quickly heat the hull to incandescent temperatures and tear it apart. Your ship's computer would need detailed three-dimensional maps of the local interstellar medium and the ability to navigate around these cosmic sandbanks, adding potentially years to a journey. This introduces another layer of navigation error. Our maps of this material are crude. We know general densities, but not the precise location of every pebble-sized bit of debris. The ship would need incredibly robust forward-looking radar or LiDAR systems operating at the limits of physics to detect hazards with enough lead time to make minor course corrections. But at 0.9 light speed, you're covering over 250,000 kilometers every second. Your detection and reaction time would need to be nearly instantaneous to avoid a dust grain spotted even a few thousand kilometers away. This is likely impossible for anything but the smallest, most agile probes. For a large crude generation ship, manoeuvring at that speed is out of the question. It would have to rely on pure statistical luck and a very heavy forward shield, accepting that over a multi-century journey a catastrophic impact is a real possibility. This transforms the risk profile of an interstellar mission. It's not just about the probability of failure at launch, it's about the accumulating risk over time, like cosmic Russian roulette. Each year of travel at high speed adds another layer of risk from an unseen impact. This has direct implications for ship design. It strongly favours smaller, tougher, unmanned probes over large, fragile, crude vessels. A probe can be built around a central hardened block of shielding with minimal exposed surfaces. It can be designed to take a hit and keep functioning, perhaps with redundant systems. A city-sized generation ship is a much bigger target, with a much higher probability of hitting something devastating over its long journey. Furthermore, the radiation environment inside the ship from the constant hail of high-energy particles would be severe, even with shielding. The secondary radiation produced when these particles slam into the hull would create a shower of X-rays and gamma rays inside the ship itself. This adds to the life support challenges for any crew, requiring even more shielding mass, which circles back to the propulsion problem. In a way, the interstellar medium problem ties all the previous barriers together. It demands enormous energy for shielding or active defense systems. It imposes strict limits on travel speed based on the density of the region you're crossing. It makes time dilation a mixed blessing, as spending more subjective time at high speed increases the cumulative number of impacts. It highlights the fragility of human biology against this particle radiation, and it underscores why robotic probes are the more sensible pathfinders. Ultimately, the void is not empty. It's a diffuse, chaotic environment that becomes lethally dense when you move through it fast enough. The dream of smoothly sailing between stars at near light speed is a fantasy that ignores the basic physics of collision. You're not sailing, you are ploughing. And the faster you plough, the harder the resistance. This is a fundamental engineering constraint that receives less attention than the glamorous issues of propulsion, but it is every bit as real. It means that even if we discover a magic engine that gives us near-light speed for free, we will still have to solve the problem of building a ship that can survive the journey through what amounts to a continuous, low-intensity particle accelerator beam. The galaxy is not only distant and expanding away. The space itself, the medium we must move through, is actively hostile to high-speed travel. It is the final, immediate environmental check on our ambitions, ensuring that the stars remain not just distant, but dangerous. After considering all the physical dangers of the journey from cosmic radiation to micrometeoroid impacts, there is another form of isolation that sets in, one that is just as absolute but less dramatic, the silence imposed by physics itself. We've talked about the speed of light as a limit for our ships, but it is equally a limit for our words, our data, our simplest hello. This creates an informational quarantine, a growing silence that severs any meaningful connection between a travelling vessel and its home, making the voyage not just a physical separation but a permanent detachment from the shared timeline of human civilization. The rule is simple. No signal, no piece of information can travel faster than light in a vacuum. This means that every communication between Earth and a starship is shackled by the same distance constraints as the ship itself. The lag is not a technical glitch to be improved, it is a law of nature. Let's start with our closest neighbour, Proxima Centauri, at 4.24 light-years away. You send a "we have arrived safely" message. It takes 4.24 years to reach Earth. Mission controllers hear it 4.24 years after you sent it. They then send a reply. Great job, now proceed with landing protocol. That reply takes another 4.24 years to travel back to you. You receive their response to your arrival message over 8.5 years after you first arrived. In that time, you've either landed, crashed, or moved on. This isn't a conversation, it's an exchange of time capsules. The concept of mission control evaporates. There is no remote piloting, no real-time troubleshooting, no timely advice during an emergency. If a critical system fails, the crew must fix it themselves, with the tools and knowledge they have on board. They cannot call for help. They cannot send a video of the problem and wait for engineers back home to devise a solution. By the time the distress signal reaches Earth and a suggested fix returns, the crisis would have been resolved one way or another decades prior. This forces a level of total autonomy that we have never required of any exploration mission. The crew, or the ship's artificial intelligence, must be the ultimate generalists, doctors, engineers, botanists, psychologists and leaders, capable of handling any conceivable problem without external input. For a multi-generational ship, this autonomy must be baked into the culture and education system. Each new generation must be able to maintain and repair systems they did not design, based on knowledge centuries old, without the original designer's guidance. This communication lag also fundamentally alters the psychology of the mission for a crewed vessel. The crew knows they're utterly alone. The comforting notion of a link to home, a psychological lifeline, is an illusion. Any message they send is a shout into a canyon where the echo returns decades later. This profound loneliness is compounded by the knowledge that everyone they knew on Earth is aging years for every month of their travel, thanks to time dilation if they're moving fast. Their personal news, births, deaths, cultural events, reaches them as ancient history. They are not participants in human society. They're archivists, receiving delayed dispatches from a past that is receding further every day. From Earth's perspective, the mission fades from public consciousness. After the initial launch, there is nothing to report for decades. The ship becomes a footnote, then a legend, then perhaps a forgotten line item in a historical database. By the time the first meaningful data returns, the civilization that launched the probe might be unrecognizable. Political systems change, languages evolve, priorities shift. A probe sent by a united Earth in the 21st century might return its data to a fragmented or entirely different human society in the 26th century. Who will be listening? Will they even know how to decode the ancient transmission protocols? The mission becomes a message in a bottle tossed into the ocean of time with no guarantee that anyone will be on the shore to catch it when it finally washes up. This lag also dismantles the scientific method as we practice it. A robotic probe arrives at an alien star system, makes a bewildering observation, say, a strange atmospheric chemistry on an exoplanet. It sends the data home. Scientists on Earth receive the data years later, analyze it, and realize they need a specific follow-up measurement to distinguish between two hypotheses. They send new instructions. The probe receives those instructions years later, but perhaps it has already moved on to the next target, or the planetary alignment has changed, making the requested observation impossible. The iterative back-and-forth process of science, where one experiment informs the next, is broken. The probe must be pre-programmed with immense intelligence and flexibility to conduct its own iterative science on the spot, making hypotheses and testing them autonomously. It needs to be a scientist, not just a data collector. For journeys to stars hundreds or thousands of light years away, the communication delay makes any two-way exchange meaningless within a human time frame. A message sent to a ship 500 light years away would get a reply 1,000 years later. This isn't exploration. It's sowing seeds for a forest you will never see. The only practical model is the fire and forget probe. You send it with a general mandate. It does everything on its own, and it beams back a torrent of data for the benefit of future generations who will piece it together centuries after the probe is dead. This communication barrier also affects navigation in a subtle way. The star charts used for the initial course are old by the time the ship arrives, because the stars themselves have moved. The ship cannot get updated, real-time positional data from Earth. It must make its own celestial observations and calculate its own corrections based on the ancient light from the stars it sees around it. It is navigating using a map of the past. Furthermore, the delay makes any kind of coordinated fleet travel, where ships support each other, incredibly difficult. Ships travelling even a few light days apart would have command delays making coordinated manoeuvres hazardous. Light from the stars it sees around it. It is navigating using a map of the past. Furthermore, the delay makes any kind of coordinated fleet travel, where ships support each other, incredibly difficult. Ships travelling even a few light days apart would have command delays, making coordinated manoeuvres hazardous. Each vessel is truly on its own. So what does this mean for the dream of an interstellar civilization? It means that any colony founded at another star will be an independent entity from day one. It will develop its own culture, technology, and political systems in complete isolation from Earth. The idea of a galactic empire with central control is a fantasy. The laws of physics prohibit the rapid flow of information necessary for an empire to function. The colonies would be separate branches of humanity, evolving independently, perhaps reuniting only after millennia of separate development, if ever. This informational isolation is perhaps the strongest argument against crude interstellar travel. Someone, someday, will remember to listen for its faint ancient whisper. In the end, the speed of light does not just limit how fast we can go, it limits how together we can be. It dictates that the universe is structured for isolated pockets of consciousness. The great silence we perceive in the cosmos, the Fermi paradox, might not be because civilizations are rare, but because they are all, by the fundamental laws of physics, rendered mute and isolated from one another, each singing its song into a void where the nearest audience lives centuries in the future or the past. Our ships may one day cross the gulf, but our voices will never keep pace. We will arrive, if we arrive at all, in silence, and we will report our findings into a silence that lasts for generations. The final frontier is not just one of distance, but of profound and irrevocable quiet. Faced with the crushing finality of the light speed limit and the silence it imposes, the human mind naturally rebels, seeking loopholes. We look to the other great pillar of modern physics, Einstein's theory of general relativity, which describes gravity not as a force, but as the curvature of space-time by mass and energy. Within this framework, mathematics allows for fantastical structures that seem to offer a way around the speed limit, wormholes and warp drives. These are not inventions of science fiction writers, they are speculative solutions to the equations of general relativity. But it is critical to understand what that really means. The math permits them in the same way the math of your bank account permits you to buy a private island. It doesn't mean the funds are there, or that the island exists. A wormhole, theoretically, is a shortcut, a tunnel connecting two distant points in space-time. Imagine the universe as a sheet of paper. The normal way from point A to point B is across the sheet. A wormhole is like folding the paper so points A and B touch, then poking a hole through the fold. You've created a bridge that bypasses the normal distance. In principle, a traveller could pass through this bridge and emerge light years away almost instantaneously, without ever locally exceeding the speed of light. The space-time inside the wormhole is its own separate piece of geometry. The problem is, according to our best models, to create and hold open a wormhole large and stable enough for anything to pass through, you would need a form of matter with what's called negative energy density, often referred to as exotic matter. Normal matter, everything we've ever seen or touched, has positive energy density. It creates gravity that attracts. Exotic matter with negative energy density would create gravitational repulsion, or anti-gravity. It's this repulsive effect that could, in theory, prop open the throat of a wormhole against its natural tendency to collapse instantly into a black hole or pinch off. We have never observed such matter. There are tantalizing quantum effects, like the Casimir effect, which demonstrates negative energy densities in a controlled microscopic way between two very close plates. But this is a tiny quantum-scale phenomenon. Scaling that up to the macroscopic level required for a traversable wormhole is like comparing a faint static shock to a planet-wide lightning storm. The amount of exotic matter required might be astronomical, possibly equivalent to the mass energy of a star or more, and we have no idea how to manufacture or collect it. Then there's the engineering, finding or creating two ends of the wormhole, stabilizing them, and ensuring the tunnel doesn't contain deadly tidal forces or random radiation that would destroy any traveller. It's a fun mathematical exercise, but a practical dead end with our current knowledge. The other famous concept is the warp drive, specifically the Alcubierre drive, named after the physicist who worked out the math in the 1990s. This idea is even more cunning. It doesn't involve moving through space faster than light. Instead, it proposes manipulating space-time itself. The concept envisions a spacecraft sitting inside a bubble of flat, normal space-time. This bubble is encased in a region of warped space-time. The mechanism would contract space in front of the ship and expand space behind it. The ship itself, inside the bubble, would be motionless relative to its local space-time. It's the bubble that moves, carried along by the motion of space-time itself. Since the speed of light limit applies to motion asterisk through asterisk space-time, not to the expansion or contraction asterisk of asterisk space-time, as we see with the universe's own faster-than-light expansion, this could in theory allow for effective faster-than-light travel without breaking local physics. It's like being on a moving walkway at an airport. You're standing still relative to the walkway, but the walkway itself is moving, propelling you forward faster than you could walk. The appeal is obvious, but once again the devil is in the details, and the details are monstrous. To create the necessary curvature of space-time, a massive contraction in front and expansion behind, you again need exotic matter with negative energy density to generate the required warp field. The energy calculations for the original Alcubierre model were absurdly high, requiring the equivalent of the mass energy of Jupiter converted entirely into energy, and later refinements still suggest needing the mass energy of the Sun or more. Beyond the energy, there are other nasty physics problems. Creating such a warp bubble would likely require forming it from a region of flat space, which might be impossible. The ship inside the bubble would be causally disconnected from the outside. It couldn't steer or stop the bubble because no signal from inside could reach the bubble walls moving faster than light. There's also the problem of what happens at the destination. The massive build-up of particles and radiation collected in front of the warp bubble during the journey would be released in a catastrophic burst of energy upon arrival, potentially sterilizing the target planetary system. Furthermore, recent studies suggest that to create the warp bubble in the first place, you might need to place the exotic matter in a region that is already moving faster than light, which is a logical paradox. So, while the equations allow it, the practical steps to get there are circular and self-defeating. These concepts highlight a crucial point in theoretical physics: the difference between something being mathematically possible and physically possible. The equations of general relativity are incredibly permissive. They allow for all sorts of strange solutions, including closed time-like curves, time travel, wormholes and warp drives. But these solutions often require conditions that violate other known laws of physics, particularly energy conditions that say matter with negative energy density cannot exist in large, stable quantities. They're considered unphysical solutions. This doesn't mean they're impossible in some ultimate sense, but it means they conflict with the rest of our understanding of how the universe works. Pursuing them is like trying to build a perpetual motion machine. It's not an engineering challenge, it's a fundamental physics challenge. You would first need to discover new physics that overturns our understanding of quantum field theory and general relativity, proving that exotic matter can exist and be manipulated on macroscopic scales. That's a revolution on the scale of moving from Newtonian mechanics to quantum theory. So where does this leave us? It leaves us with a clear but frustrating distinction. Wormholes and warp drives are not technologies waiting for better materials. They are theoretical curiosities that point to the edges of our understanding. They're important because they show where our models break down or become strange, and studying them can lead to deeper insights into gravity, quantum mechanics, and the nature of space-time. But they are not blueprints. To invest in them as the solution to interstellar travel is, at this moment in history, equivalent to investing in alchemy as the solution to material science. It's hoping for a miracle. The sobering truth is that all our viable, near-term concepts for interstellar travel, solar sails, fusion rockets, even antimatter engines, accept the light speed limit. They work within the known laws, trying to inch us as close to that limit as possible, accepting the long travel times. The speculative physics offers a dazzling dream of a universe where the rules are different, where the galaxy is a neighbourhood you can pop across for a visit. But our universe, as far as we have been able to measure and test, appears to be the other kind. The kind with a strict speed limit, vast distances and no shortcuts. The true work of interstellar travel, if it is ever to become more than a dream, lies in the grinding, incremental engineering of systems that can survive and propel themselves across the void within those strict rules. It's less glamorous than a warp drive, but it's the universe we actually have. The speculative concepts serve as a reminder of our creativity and our hope, but they also, by their extreme difficulty, reinforce the immense challenge set before us by nature. They are the ultimate what if, but not for now, a how to. The idea of waiting for a better idea, a more elegant solution, is deeply human. It's why we hesitate before buying a new phone, knowing next year's model will be faster. But in interstellar travel, this hesitation isn't just about minor upgrades. It's a fundamental paradox that could freeze any real progress in its tracks. Imagine we decide as a civilization to commit to a massive project, a generation ship. We pour decades of resources into designing and constructing a vessel capable of sustaining a community for a journey of, say, 200 years to a nearby star. It uses the best technology we have in the 21st century, perhaps efficient nuclear fusion propulsion, advanced closed-loop life support, and robust radiation shielding. It launches with great fanfare, carrying the hopes of humanity into the void. The crew settles in for the long haul, their descendants destined to complete the mission. Now, fast forward 50 years after launch, back on Earth, technology has not stood still. Research into breakthrough propulsion concepts, fueled by advances in materials science, artificial intelligence, and energy production, has borne fruit. A new propulsion system is perfected, perhaps a scaled-up version of a laser sail system that can accelerate smaller, smarter probes to 30% of light speed, or a breakthrough in antimatter containment that allows for a much faster, albeit still robotic, vessel. This new technology is developed, tested, and launched. Because it is faster, this second mission, even though it started half a century later, could theoretically arrive at the same star system decades or even a century before the original generation ship. The first ship, carrying living, breathing humans who have lived and died for the mission, arrives to find their destination already surveyed, maybe even with robotic outposts established by the later, faster mission. Their entire epic journey, their sacrifices, their culture built around this goal is rendered historically quaint, a footnote. This is the paradox of obsolescence. It creates a perverse disincentive. Why commit to a multi-generational, civilization-spanning project with today's technology when waiting a century might yield technology that makes the trip in a fraction of the time with a fraction of the risk and cost? The logical conclusion seems to be, always wait. The next century will always have better tech. But if you follow that logic forever, you never launch anything. It's a trap. This paradox strikes at the heart of long-term planning. It is most severe for crewed missions, given their immense complexity and cost, but it even applies to robotic probes. If you launch a slow, massive probe with a giant suite of instruments, a faster, cheaper, more capable probe launched later could overtake it and send back data first, making the initial investment seem wasteful. This isn't just speculative. We see a mild version of this in solar system exploration. Newer missions often have better instruments and more sophisticated software than those launched just a few years prior. The difference is that within the solar system, travel times are years, not centuries, so the lag isn't as dramatic and missions can have distinct complementary goals. For interstellar trips, the timescales are so long that the technological evolution on Earth is potentially revolutionary. This creates a strategic dilemma. Do you commit to a slow and steady path, building and launching what you can with current knowledge, accepting that it may be obsolete upon arrival? Or do you adopt a wait for the breakthrough stance, focusing all efforts on fundamental research into physics and propulsion, hoping for a game changer like a functional warp drive before building anything? The latter seems smarter, but it risks never building anything at all, as breakthroughs are unpredictable. There is no guarantee a breakthrough will ever come. The wait could be 1,000 years. Furthermore, the process of building the slow ship itself generates technological spin-offs and practical knowledge that might be essential for developing the fast technology later. You learn how to build closed ecosystems, manage long-term space habitation, and handle the psychological aspects of isolation. These are not trivial problems, and solving them for a generation ship could provide the necessary stepping stones for faster missions later, even if the generation ship itself is ultimately outpaced. So perhaps the answer isn't a binary choice, but a layered approach. You pursue fundamental research into breakthrough physics aggressively, while also executing incremental, ambitious missions that push the boundaries of known technology on shorter, but still interstellar scales. For example, a concerted project to build a massive laser array in the solar system, to propel gram-scale starships to Alpha Centauri at 20% of light speed is a near-term goal based on known physics. It would take decades to build, and the probes would take about 20 years to get there. While that project is underway, research into fusion, antimatter, and even speculative physics continues. The data from the Starship mission would be invaluable, and arriving in a human lifetime, it wouldn't suffer the full obsolescence paradox. This incrementalism builds capability and momentum. It also changes the economic calculus. A giant generation ship is a one-off, all-or-nothing monument. A laser array infrastructure once built can launch many missions to many stars, with regular upgrades to the probes it launches. The launch infrastructure itself becomes the lasting asset, not the individual probes. This mitigates the paradox because the infrastructure can be improved over time, launching ever better probes without being rendered completely obsolete. The array you build in 20 years might be less efficient than one you could build in 50 years, but it's already operating, gathering data and funding its own upgrades. Another angle is to embrace the obsolescence for crewed travel, but frame it differently. A generation ship might not be just a means to an end, it could be an end in itself, a permanent mobile habitat, a branch of humanity that lives in space. Its goal isn't solely to reach a specific star, it's to survive and thrive as a spaceborne civilization. Reaching a star becomes a bonus, a resupply point, not the sole purpose. This reframing sidesteps the paradox, because the journey is the life, not a prelude to a life. The technology on board evolves as best it can, but the community's purpose is intrinsic to its existence on the ship, not contingent on beating a later probe to a destination. Ultimately, the paradox of obsolescence is a conflict between human timescales and cosmic ones. Our technological progress moves quickly, star travel, with known physics, moves slowly. The paradox forces us to think about the purpose of exploration. Is it purely about the destination, the data from a specific star? If so, then waiting for the fastest possible probe is logical, but it may mean we never go, always holding out for a better tomorrow. Or is it about the act of going itself, about extending our presence and capabilities step by step into the cosmos, learning as we go, even if our first attempts are slow and clumsy? The history of exploration on Earth suggests the latter. The Polynesians didn't wait for modern navigational satellites to spread across the Pacific. They used the best technology they had, outrigger canoes and knowledge of stars and waves, and they went. Later, faster ships followed, but the first voyages were no less meaningful. Their courage and skill built the knowledge base that made later, more efficient exploration possible. In the interstellar context, our outrigger canoe might be a laser-sailed microprobe. It's a first, tangible step. The data it returns, the lessons learned from building the infrastructure to launch it, make the next step, perhaps a larger probe, then a slow robotic surveyor, then perhaps a frozen hibernation crewed mission, more feasible. The paradox warns us against monolithic dead-end projects that lock in obsolete technology for millennia, but it should not paralyze us. It should guide us toward flexible, incremental, and infrastructure-based approaches. It tells us that the first interstellar missions should be numerous, cheap, and fast to develop, so that if they're overtaken, the loss is not catastrophic. It tells us to build launch systems that can be upgraded, and most of all, it tells us that the journey of becoming an interstellar species is not a single race to a finish line, but a slow, patient migration, where each generation builds a little more of the road, even if they never see its end. The fear of obsolescence is the fear of our own progress, but that progress is precisely what might one day get us there. The logical conclusion from all these compounding challenges, the energy cost, the time dilation, the biological fragility, the social complexity of generation ships, and the paradox of obsolescence, is not that we should give up on reaching the stars. It's that we must fundamentally reconsider who or what we send. The romantic vision of brave astronauts piloting a ship to a new world is powerful, but when you run the numbers, when you weigh the risks and costs, a clear and pragmatic favourite emerges: the machine. Robotic probes are not just an alternative. They are, by a staggering margin, the only realistic option for interstellar exploration within any foreseeable future. Think about the advantages, starting with the most basic. A robot doesn't need to breathe. It doesn't need food, water, or a constant, perfectly balanced atmosphere. It doesn't get osteoporosis in microgravity or suffer irreversible DNA damage from cosmic rays at the same rate as living tissue. It doesn't experience loneliness, depression, or cabin fever. It can be switched off for decades of a journey, hibernating in a state of minimal power consumption and then awakened with a timer or a signal. This eliminates the need for the single most massive and complex system on a crewed ship, the human life support infrastructure. That means the entire vehicle can be smaller, lighter, and vastly simpler. The propulsion energy required to send a 1-ton robotic probe to 10% of light speed is a fraction of that needed for a 1,000-ton generation ship. The difference isn't linear, it's exponential. This makes the mission potentially affordable, or at least conceivable within the energy budget of an advanced planetary civilization. We have proof of concept already hurtling through the void. The Voyager probes, the Pioneers, New Horizons. These are our first interstellar travellers, albeit slow ones, who carry no life support, just instruments, computers and power sources. They have operated for decades, sending back priceless data, and they will continue drifting among the stars for eons. They are the blueprint, just on a slower timescale. The next step is to add speed. Projects like Breakthrough Starshot envision this clearly. Use a powerful ground-based laser array to propel a fleet of gram-scale starships attached to lightweight sails to Alpha Centauri at 20% of light speed. These would be true interstellar probes, reaching another star in a human lifetime. They would carry micro-scale cameras, spectrometers, and communications lasers. They would fly by their target at incredible speed, snapping pictures and collecting data in a frantic rush, then spend years beaming that precious information back to Earth. This is not science fiction, it's an engineering project with identified challenges, but no laws of physics need to be broken. The key is that every gram counts. The human crew is measured in tens of thousands of kilograms. A sophisticated microprobe is measured in grams. The scale difference is the difference between impossible and possible. Furthermore, robots can be hardened against the space environment in ways biology never can. Shielding a delicate computer chip from radiation is easier than shielding an entire human nervous system. You can use redundancy, multiple copies of critical systems, so that if one component is fried by a cosmic ray, another takes over. A probe can be designed to endure the brutal bombardment of the interstellar medium at high speed with a sturdy ablative shield, whereas a human cabin would need to be protected to a far greater degree. Robots also solve the problem of time. They don't care about subjective time or generational legacies. A probe on a 200-year journey is just a machine fulfilling its programming. It has no anxiety about the passing years, no fear of mortality, no confusion about its purpose. It simply goes, sleeps, wakes up, works, and reports. This makes missions of any duration feasible. We could send probes on 1,000-year journeys to interesting star systems at 100 light-years away, knowing that someday a future civilization will get the data packet. This patience is a superpower machines have that we lack. Autonomy is the next critical piece. With communication delays of years, a probe must make its own decisions. This is where artificial intelligence becomes not just helpful, but essential. The probe's AI would need to handle navigation corrections, manage its own power and health, prioritize scientific targets upon arrival, and respond to anomalies, all without a word from Earth. We are already developing such autonomy for Mars rovers, where commands have a delay of minutes. Scaling that up to a light-year scale delay is a software and AI challenge, but again, not a physics-breaking one. We can imagine a probe arriving at a distant planetary system, its AI acting as a scientist in situ, identifying interesting phenomena, deciding which moon to examine closer, adjusting its sensor suite on the fly to investigate an unexpected atmospheric signature. It would be our intelligent, resilient proxy. Then there is the concept of replication, a controversial but theoretically powerful idea. A von Neumann probe is a hypothetical, self-replicating spacecraft. It would travel to a star system, use local resources, asteroids, moons, to build copies of itself, which would then launch to more star systems. The process could, in theory, allow a single probe to explore the entire galaxy in a surprisingly short cosmological time, a few million years, which is a blink compared to the galaxy's age. The ethical and existential risks of such technology are immense. It could be seen as a galactic plague, consuming resources, and potentially outcompeting any natural life. but from a purely logistical standpoint, it represents the ultimate expression of machine-based exploration, sustainable, exponential, and independent. It highlights that machines, not biology, are the medium best suited for indefinite expansion into a harsh, resource-scattered environment. This isn't to say human curiosity is irrelevant, quite the opposite. Every bit of data the probes send back fuels our human desire to know and see. We would experience the exploration through their digital eyes. With advancements in virtual reality and haptics, we could one day walk on an exoplanet's surface through a immersive reconstruction built from probe data, feeling the crunch of alien gravel under our virtual boots without ever risking a life. The exploration becomes vicarious but no less profound. The dream of setting foot on an alien world is powerful, but it may be a luxury or a final step, not the first step. The first waves will be silent, patient, and made of metal and silicon. They will be our scouts, mapping the way, assessing the dangers, and telling us what's out there. Only after they have sent back detailed reports about a truly welcoming Earth-like world might we then contemplate the infinitely more complex task of sending something as delicate as a human being. And even then, it might be more sensible to send frozen embryos or artificial wombs, guided by machines, to found a colony without the perilous journey for living adults. In the end, the argument for machines is an argument for playing to our strengths. Our strength as a species is not our physical durability in space. It's our intelligence, our ingenuity, our ability to build tools that extend our senses and our reach. The interstellar probe is the ultimate tool. It is the embodiment of our curiosity, stripped of our biological limitations. It accepts the harsh rules of the universe, the light speed limit, the vast distances, the hostile medium, and works within them. It doesn't try to cheat physics with warp drives. It uses physics in the form of focused light or nuclear propulsion to push the boundaries of the possible. Choosing machines is not a surrender of the dream. It's the maturation of the dream. It's the recognition that the galaxy is not a frontier for pioneers in the classical sense, but a realm of information to be gathered and understood. Our human bodies may be forever tethered to Earth's gravity well, or at best to a few localized outposts in our solar system. But our minds, through the proxies we build, can roam the entire Milky Way. The future of interstellar exploration, therefore, likely belongs not to bustling star cruisers with human crews, but to silent, dark, intelligently designed artifacts, coasting between the stars for centuries, carrying the focused will of a species that chose to see rather than simply to go. Accepting that our emissaries to the stars will likely be machines made of silicon and steel rather than flesh and blood doesn't entirely quiet a deeper, more unsettling line of questioning. It simply pushes it one step further back. Why? Why is the universe structured this way? Why is there a fundamental speed limit that seems to lock civilizations into their own solar neighborhoods, or at best their own galactic clusters? This isn't just a technical frustration. It feels like a cosmic condition, a rule that carries a weight of intention, even if none exists. We are forced to confront the possibility that the light speed barrier isn't just a random fact of physics, but something with implications for our place in the cosmos. Is it a prison, a protection, or simply a test? Let's start with the simplest interpretation. It's an accident. The speed of light, c/c, is a constant that falls out of the equations describing electromagnetism and space-time. It could have been different. In some hypothetical other universe, the speed limit might be higher, lower, or non-existent. We just happen to live in a universe where it is 299,792,458 meters per second. In this view, there's no deeper meaning. It's like gravity being a certain strength. It's just a parameter. The vast distances and speed limit together create a universe that is, for all practical purposes, mostly empty and mostly inaccessible. Intelligent life, wherever it arises, bumps into this same wall. It's not personal, it's just geometry and physics. This is the cold, indifferent universe of pure scientific materialism. Yet, the consequence of this accident is profound. It effectively quarantines civilizations. Think about it. If you cannot travel faster than light, and the nearest star system is years away even at that speed, then any two civilizations are separated by a gulf of time as well as space. Communication takes generations. Travel takes millennia. This makes conflict between star systems absurdly impractical. Why would you launch an invasion fleet that would take centuries to arrive, by which time the defending civilization would have seen it coming for hundreds of years and could have prepared or simply moved? The energy cost alone would be prohibitive. The speed of light combined with distance acts as the ultimate peacekeeper. It prevents the rapid spread of potentially hostile or destructive cultures. It allows civilizations to grow and develop in isolation, without fear of immediate subjugation or annihilation from a more advanced neighbour. In this light, the barrier looks less like a prison wall and more like the ocean that separated continents on Earth, allowing distinct ecosystems and cultures to develop independently. It's a form of cosmic biodiversity protection. This ties directly into potential solutions to the Fermi paradox. Where is everybody? Or perhaps they're all at home, trapped just like us, looking out at the silent stars and wondering the same thing. The zoo hypothesis, or the planetary quarantine idea, suggests that more advanced civilizations might deliberately avoid us. But a simpler answer is that physics itself enforces the quarantine. The Great Silence isn't due to a lack of life, but a lack of a viable medium for chatter and travel across the interstellar distances. Everyone is whispering, but the room is the size of a continent and filled with noise. No one hears anyone else. There is another, more existential take. Perhaps the limit is a test, or at least a filter of a different kind. To overcome the limitation of light speed, a civilization would need to master physics at a fundamental level. It would need to harness energies on a stellar scale, create perfectly closed ecological systems for generation ships, or perhaps discover loopholes in general relativity that require a profound unification of quantum mechanics and gravity. This isn't just an engineering challenge. It's a test of a species' maturity, patience, and collective intelligence. A species that remains fractious, short-sighted, and planetary bound will never pass it. A species that learns to cooperate on a global scale, manage its home planet sustainably, and invest in long-term scientific projects spanning centuries might eventually develop the technological sophistication to reach the stars, albeit slowly. In this view, the light-speed barrier isn't a wall to be knocked down, but a mountain to be climbed. The journey itself forces the development of a stable, wise, and advanced civilization. The physicist David Deutsch, among others, argues that limits we once thought were absolute have a history of being overcome through new knowledge. He would likely see the light speed limit not as a final barrier, but as a challenge to our current understanding. The lesson from history is that when we hit a seemingly absolute limit, it often means our model is incomplete. The transition from Newtonian mechanics to relativity is the classic example. So perhaps the limit of light speed for massive objects is a feature of our current theory, not of the universe itself. The hope, then, is for a new synthesis, a theory of quantum gravity that reveals how to manipulate space-time in ways that seem like magic to us now. But this is hope, not a plan, and it's a hope that has persisted for decades without a breakthrough, which leads to a final, more introspective possibility. Maybe the limit is guiding us toward a different kind of exploration altogether. If physical travel to the stars is so monumentally difficult, perhaps the universe is steering intelligent life toward exploring inwardly, through intellect, simulation, and enhanced perception. Our greatest tool is not the rocket, but the mind. With telescopes we can analyse the atmospheres of distant planets. With particle colliders, we probe the fundamental forces. With computers, we can simulate cosmic evolution or model alien biospheres. The next step might be to merge with our technology, enhancing our cognitive abilities to perceive and understand the universe in ways that render physical travel less relevant. Why brave a 1,000-year journey to see an alien sunset when you can experience a perfect data-rich simulation of it? Or when your expanded consciousness can grasp the beauty of its physics from light years away? The exploration becomes informational and experiential rather than physical. The limit, then, becomes a catalyst for evolutionary shift from a biological planetary species to a potentially post-biological informational one. Our destiny might not be to spread our bodies across the galaxy, but to spread our consciousness, our knowledge, and our art, encoded in light beams or subtle manipulations of space-time we can't yet imagine. So, is the light speed limit a barrier or a protection? It is likely both and neither. It is a physical fact. Its interpretation depends entirely on our response, If we see it as a prison, we may rage against it and expend our civilization's resources in a futile attempt to break the unbreakable, potentially collapsing in the process. If we see it as protection, we might relax into our cosmic isolation, focusing on making our own planetary home a paradise, but perhaps surrendering the grand human ambition to connect with something greater. If we see it as a test, it gives our technological and social development a profound goal: to become a species worthy of the stars, not through conquest, but through understanding and perseverance. And if we see it as a guide, it redirects our energy from building faster ships to building smarter minds and richer inner experiences. In the end, the universe doesn't care. The constant C is just a number, but we care. And in our caring, in our struggle against this limit, we define who we are. The barrier forces a choice. Do we turn outward with brute force or inward with greater wisdom? The history of life on Earth suggests that adaptation is more successful than sheer force. The organisms that thrive are not always the strongest, but those that best understand and fit into their environment. Our cosmic environment is one of vast distances and a strict speed limit. Adapting to that might mean embracing the role of the observer, the thinker, the simulator, and the creator of meaning, rather than the conqueror of territory. The stars may forever be out of physical reach, but they are already within our intellectual and imaginative grasp. That, perhaps, is the real gift of the limit. It didn't give us an easy galaxy to colonize. It gave us an infinite puzzle to solve, a perpetual horizon to strive toward, and a reason to become smarter, wiser, and more unified than we are today. The final frontier might not be space, but the potential of the mind that contemplates it. So after wrestling with the philosophy of limits and the promise of machines, we come down to perhaps the most mundane yet most formidable barrier of all, the checkbook and the committee meeting. Even if we somehow solve the physics, the engineering and the biological puzzles, we are left with a question that has stymied grand human endeavours for millennia. Who pays for it, and who stays committed to it for the centuries required? An interstellar mission, particularly a crude one, wouldn't just be a scientific project. It would be the defining megaproject of our species, a civilization-scale undertaking that would demand unwavering focus and resource allocation across generations. This is where the rubber meets the cosmic road, and the road is made of economic spreadsheets and political will, both of which are notoriously unstable over long periods. Let's start with the sheer economic scale. Building a ship capable of ferrying humans to another star, or even a massive robotic ark, would consume a significant portion of a planet's economic output for decades, maybe centuries. We're not talking about a percentage of a space agency's budget. We're talking about a percentage of global GDP. Imagine diverting the equivalent of the combined military budgets of every nation, or the total investment in global infrastructure, into a single project with no return on investment for hundreds of years. The opportunity cost is staggering. Those resources, raw materials, intellectual capital, industrial capacity, would not be available to solve pressing problems on Earth. Climate change mitigation, poverty alleviation, healthcare, education, environmental restoration. The political and ethical debate would be intense. Proponents would argue for the long-term survival and expansion of humanity. Opponents would argue it is the ultimate in reckless spending, a multi-generational vanity project that steals from the immediate needs of the living. Could any government or consortium of governments ever justify such an allocation to its citizens, who want better lives now, not a star probe their great-great-great-grandchildren might hear from? This leads directly to the problem of political continuity. Human political systems are volatile on century timescales. The nation that champions the project at its inception might not exist 100 years later. It could fragment, be conquered, undergo revolution, or simply change its priorities with a new election or regime. The International Space Station Partnership has held for decades, but it exists in a relatively stable geopolitical context and with a modest budget. An interstellar project would be a vastly larger bet. A new administration or a new ruling party could see it as a waste and cancel it, wasting the investment of previous generations. History is littered with unfinished cathedrals and abandoned grand projects because the king died or the money ran out. For a project whose construction phase might last longer than the lifespan of most nations, this is a near certainty. The project would need to be insulated from political winds, perhaps managed by a quasi-independent global trust with its own funding mechanism, something akin to a permanent endowment. But creating such an entity requires a level of global trust and governance that we simply do not possess today. Then there is the social and psychological commitment. A generation ship project would require not just funding, but people, thousands of engineers, scientists and workers dedicating their entire careers to a project whose launch they will never see. Their children would then have to take up the same work, and their children after them. This demands a cultural narrative of extraordinary power, one that can instill a sense of purpose and destiny across centuries. It would need to become a central pillar of civilization's identity, as powerful as a major religion or a timeless cultural artifact. Our current society, with its rapid news cycles, short-term financial incentives, and shifting cultural trends, is not built for this. We struggle to maintain infrastructure built 50 years ago. Could we maintain focus on a single goal for 500? The answer, based on our history, is probably no. We have few examples of truly multi-generational projects. Medieval cathedrals took centuries to build, but they served an immediate religious and community function at every stage. They were part of the fabric of daily life. An interstellar ship being built in orbit or at a Lagrange point would be abstract, distant and invisible to most people on Earth. Its completion would be a theoretical event in a far future. Maintaining public support and skilled labour pipelines for such an abstract, long-term goal is an unprecedented social challenge. Furthermore, there is the ethical question of commitment for those not yet born. By launching a generation ship, the founding generation makes a choice that binds countless future generations to a life in confinement, to a mission they did not choose. We consider it unethical to impose major, life-altering choices on our children without their consent. Is it ethical to impose an entire civilization's destiny on thousands of descendants? The counter-argument is that all parents make choices that affect their children's lives, where they live, what culture they're born into. But the scale is different. This is a deliberate, premeditated choice to create a lineage with a single, inescapable purpose. It is a profound act of intergenerational engineering that many would find morally questionable. Finally, there is the sheer risk of catastrophic failure. From an investor's perspective, it's a terrible bet. You spend a civilization's treasure for centuries, and the ship could be destroyed by a micrometeoroid swarm, a critical system failure, or internal social collapse 100 years into its journey with nothing to show for it. The potential for total, irrecoverable loss is gigao. This risk makes it incredibly difficult to secure the initial investment. On Earth, high-risk projects can attract venture capital because the potential payoff, while uncertain, is relatively near-term. Here the payoff is so distant and uncertain that no traditional economic model supports it. The project could only be justified on non-economic grounds: species survival, the pursuit of knowledge, or the fulfillment of a cosmic destiny. These are powerful motivators, but are they powerful enough to override our innate short-termism and risk aversion? In light of all this, the most likely path for an interstellar mission is not a sudden Apollo-style giant leap, but a slow, creeping expansion of our economic and industrial sphere into the solar system. If we become a truly spacefaring civilization, with large-scale industry on the Moon, Mars and the asteroid belt, then the economic equation changes. The resources for an interstellar ship would not come from Earth's strained budget, but from the abundant material and energy resources of space itself. The construction would be a major project, but one undertaken by a post-planetary society with a vastly greater resource base. The political entity authorizing it might be a solar system-wide consortium, more stable than any earthbound nation. The people building it would be space dwellers, for whom space engineering is the norm. In this context, an interstellar ship becomes a logical, though still monumental, next step. It becomes an export of a space-based culture, not a desperate gamble by a planetary one. Therefore, the economic and political barrier is not just about money and willpower, it's about evolutionary stage. A civilization that can build an interstellar ship is, by definition, one that has already mastered its own solar system, achieved long-term stability, and learned to think and invest on timescales of centuries. We are not that civilization. Our debates about interstellar travel are in a way premature, and we are putting the cart before the horse. The real first step towards the stars isn't designing the warp engine, it's learning to live sustainably on Mars, harvesting asteroids, and building a society that can plan beyond the next election or quarterly report. The financial and political viability of an interstellar mission will be a symptom of our maturity as a species, not a cause of it. Until then, the dream will remain just that. A dream limited not by the laws of physics, but by the fickle nature of human economics and politics. The final and perhaps most humbling barrier to the stars is our own current nature. So, if the ultimate barrier is our own nature, our short-term thinking, our economic limitations, our political volatility, then perhaps the solution is to redefine the goal itself. What if the pinnacle of exploration doesn't require moving our bodies at all? What if, instead of fighting the physics of light speed and the economics of generation ships, we embrace a different kind of journey, one of perception, simulation and pure intellect? This is the frontier that is already opening before us, and it may represent not a consolation prize, but the actual logical evolution of how a curious species comes to know its universe. It is exploration without movement, and it is already revolutionizing our understanding of everything. Consider the telescope. It is the ultimate tool for this kind of exploration. We are living in a golden age of astronomical observation. The James Webb Space Telescope is not a ship. It's a time machine and a chemical analyzer parked 1 million miles from Earth. It collects ancient light that has travelled for billions of years. With it, we are not just seeing distant galaxies, we are dissecting the atmospheres of planets orbiting other stars. We can detect water vapour, methane, carbon dioxide, and even potential biosignatures like dimethyl sulfide, all from a distance of hundreds of light years. This is exploration. It is remote sensing on a cosmic scale. Every new telescope, from ground-based extremely large telescopes to future space-based observatories, extends our vision further and in more detail. We are mapping the cosmos in unprecedented fidelity, discovering exoplanets by the thousands, watching stars being born and dying in nebulae, and probing the structure of space-time itself through observations of gravitational waves. This is not a passive activity. It is active, thrilling discovery. We are exploring, just with photons instead of rockets. The data from these telescopes then feeds the next tool, the supercomputer. With enough computational power and the right physical models, we can simulate the processes we observe. We can simulate the formation of a galaxy from a cloud of dark matter and hydrogen after the Big Bang. We can simulate the chaotic collisions that built planets. We can simulate the climate of an exoplanet with a certain atmospheric composition and star type, predicting its weather patterns, ocean currents, and potential habitability. These simulations are virtual laboratories where we can run experiments impossible in the real world. What happens if you tweak the strength of gravity? What if dark energy behaved differently? We can create and explore a multiverse of hypothetical universes, all from a server farm. This is a form of exploration as well, probing the space of possibilities allowed by physics. It deepens our understanding of why our universe is the way it is. Then, there is the burgeoning realm of virtual and augmented reality. This is where the experience of exploration becomes personal and immersive. Imagine putting on a headset and standing on the surface of Mars, not as a flat panorama, but as a fully three-dimensional, geologically accurate environment built from rover and satellite data. You could look at the rocks, see the layers in the canyon walls, watch a simulated dust devil pass by. The data is real, the experience is constructed. Now extend that to an exoplanet. Using atmospheric data and geological principles, you could generate a plausible, walkable environment for Proxima Centauri b. You could experience the ruddy light of its star, feel the pull of its higher gravity, look up at its strange sky. It would be an exploration driven by real science, but delivered as an experience. For the public and for scientists, this could be transformative. It makes the cosmos accessible in a way a graph of atmospheric spectra never could. It fulfills the human desire to be there without the million-year journey. Furthermore, as our understanding of physics deepens, we might explore realms that are inherently unreachable by any physical probe. The interiors of black holes, the conditions of the universe's first second, the nature of extra dimensions predicted by string theory. These are domains where physical travel is nonsense, but where mathematical and simulated exploration is the only path to knowledge. We explore them with equations and visualizations. This is not a lesser form of discovery, it is the only form possible for such realms. It is the mind extending its reach where the body can never follow. This shift from physical to informational exploration also aligns perfectly with our likely future as a species intertwined with artificial intelligence. An AI does not have a body to transport. Its exploration is the ingestion and analysis of data. It can study the entire electromagnetic spectrum simultaneously, find patterns in petabytes of telescope data invisible to us, and generate hypotheses at lightning speed. Our partnership with AI will likely define this new age of exploration. We will provide the curiosity and the questions. The AI will provide the data processing power, and perhaps even the intuitive leaps, guiding our telescopes and refining our simulations. Together, we will explore a universe of information. Some might argue this is all just a fancy way of giving up, of accepting a cosmic cage. But that misses the point. The goal of exploration is knowledge and experience. If you can gain the knowledge and a faithful, immersive experience of a place without undertaking a perilous and multi-generational voyage, is that not a wiser, more efficient path? It is the difference between spending a lifetime and a fortune to climb a remote mountain once and using satellite imagery, drone footage, and detailed geological surveys to understand that mountain completely and even simulate the climb in perfect detail. The latter approach allows you to understand not just one mountain, but all mountains. The resources saved can be used to understand other things. This model also solves the economic and political barriers almost entirely. Building a new telescope or a faster supercomputer is expensive, but it is a fraction of the cost of an interstellar ship. The benefits are immediate. New scientific discoveries, technological spin-offs, and public engagement. The funding cycles are within the scope of decades, not centuries. The project can survive changes in government. It is a sustainable model of exploration that fits within our current human limitations. It allows us to satiate our curiosity and expand our knowledge continuously, building a cumulative understanding of the cosmos without waiting for a mythical future technology or a transformation of human nature. This is not to say we should abandon all thought of physical travel within our solar system. That is a necessary and thrilling endeavour for resource gathering, science, and perhaps even colonization. But for the true vastness of the galaxy and beyond, the most profound and realistic exploration may happen right here, in the orbit of our planet and within the circuits of our computers. We will explore the universe by bringing its light to us, and by building perfect virtual copies of its wonders. The final and perhaps most profound exploration may be an inward one, exploring the power of our own intellect and technology to comprehend the whole. The journey becomes not a physical traversal of space, but a cognitive traversal of understanding. In that sense, the stars are not distant points we must painfully reach. They are data streams we must learn to decode, and simulations we must learn to build. The universe is not a destination, it is a data set, and we are only just beginning to learn how to read it.